Hello, this is Mr. Gilmore with the 5.4, the Hinge Theorem and its Converse lesson. Now, we have seen comparisons within one triangle, right? We've been able to compare sides of the same triangle, angles of the same triangle, but now we want to actually broaden our comparisons and say, can we actually compare with pairs of triangles, meaning one side of one triangle to another side, or a pair of angles that belong to one triangle and the other to the another triangle? So the question is, are we able to do this? And the answer is yes. However, it's not in every case. We actually have to have something specific given to us about the pairs of triangles in order for us then to cross compare between the two triangles. Before we get into our Hinge theorem and converse of Hinge today, let me remind you of one very important property that we have with the relationship of greater than. We have the transitivity of greater than, which says that for all quantities A, B, and C, if A is greater than B and B is greater than C, then in fact A is also greater than C. We will utilize this property today when we get into the proof of Hinge theorem. So let me introduce you to the Hinge theorem, right? Here's what it states. If two sides of one triangle are equal to two sides of a second. Now, pause there for a moment. Notice that we already have this equal relationship going on between the two triangles, that two sides of one are equal to two sides of the other. And the included angle in the first is greater than the included angle in the second. So keep that in mind. We now have a comparison of angles. So, and not just any pair of angles, but the included angles. These must be the angles that are sandwiched between the pairs of equal sides. So again, there's a lot of stipulations going into the condition, or this given of the conditional for Hinge theorem that we have to satisfy. We can't just cross compare between any two triangles. So let's read that given one more time. If two sides of one triangle are equal to two sides of another, and of the second, and the included angle of the first is greater than the included angle of the second, then the third side of the first is greater than the third side of the second. In other words, we can actually look across where our included angle is to the third side, and we can actually cross compare those two sides. That the greater side will be opposite that greater angle, but you have to have this full given satisfied before you can even remotely compare those two sides together. Let's bring the Hinge theorem to life into an illustration. So here we have two triangles, ABC and DEF. We're given that two sides of one triangle are equal to two sides of the other. AB is equal to DE, BC is equal to EF, and we're also given the comparison of our angles, that angle B is in fact greater in measure than angle E. Let's then conclude that AC is greater than DF. So the side opposite of our included angles here, we can compare them. Right, we can actually compare AC, and we'll say that AC is in fact greater than DF. That is what we're going to prove. Okay, that's what we're going to prove. Now, when we jump into this proof, it has quite a unique construction to it. So let me walk you through our constructions first, and then we'll jump into the proof. The proof is a bit tricky, which is why I'm going to guide you through this in the video notes here. So where our construction begins is, since we are given that angle B is greater than angle E, that means we can measure and make measure. In other words, I'm going to measure out my angle B. And what I'm going to do is, using side DE, I'm going to create an angle that's equal to angle B. In other words, I'm going to use DE as one side and then create an angle here that is also equal to angle B. In other words, I've got angle ABC, or angle B, is equal to angle DEG. Okay, so I've created this ray EG such that the angle formed there is equal to angle B. I'm allowed to do that, measure, make measure. And I know that angle B is greater, which means I know that it will pass over angle E completely. Now, where I stop my ray, EG, is also a strategic construction. Since that ray EG is kind of jutting out there, I truncated it at point G such that it's equal in length to our given side, EF. In other words, if you take a look, E to G and E to F are equal in length, and we were given that B to C is equal in length. So we know that all three segments there are going to be equal in length, BC, EG, and EF. All three segments now are equal in length. The last bit of constructions are very simple. You simply just connect point G to point F and point G to point D. Now, where our focus is going to then turn, we're going to actually progress through several different triangles, but where we want to end up is actually in this last triangle that's formed down here below. That's where we want to end up, okay? Because I want to be able to compare these sides, AC and DF. Remember, the claim is that AC is going to be greater than DF, okay? Those are the two sides we're focused on. However, to get there, what I'm going to do is have to actually have a comparison of angles. And so I'm going to find that DF here, this angle here, DFG, this angle formed, I can prove it greater than angle DGF, this angle right over here. That's our goal. If we can prove that angle DFG is greater than angle DGF, then we can cross compare the sides, and that's going to carry us into our final conclusion that AC is going to be greater than DF. Okay, now this proof is a bit tricky, which is why I'm going to guide you through this one. So let's take a look. So we've got our two diagrams again, post-construction, which means post-construction we know that BC is equal to EF, which is also equal to EG. So all three of those are equal to each other, and we're also, by our construction, know that angle B is equal to angle DEG. Okay, so where we actually begin is we, from our construction, have formed a pair of congruent triangles. Triangle ABC is congruent to triangle DEG. Why? Well, because we have two sides of the first equal to two sides of the second, and the included angle of the first is equal to the included angle of the second, which means by side angle side congruence, we have ourselves a pair of congruent triangles. Now, why is that important to us? Because I need to relate the side AC to a new segment that was formed on the other diagram, side DG. So I can claim that AC and DG are equal to each other by our good pal CPCTE. Now, where are we going? We're going to turn our attention onto a specific triangle, and then we'll be looking at comparing angle measures. So the triangle I want to focus on next is triangle EFG. Find triangle EFG. Notice something special about it. Right? By our construction, EF and EG are equal, which means we have an isosceles triangle, EFG, which means I can claim that the base angles here of our isosceles are in fact equal in measure, that angle EFG and angle EGF are equal. And why? That's by our good old pal ITT. All right. Now we turn our attention to angle comparisons. Because I know something about angle DFG. Take a look at angle DFG. That's a whole angle, but if we look at our diagram, it's cut into smaller parts. There's an angle DFE and an angle EFG. Okay, so what's important about those? Well, I know that DFG being the whole is greater than any of the parts. So DFG is greater than angle EFG, and I know that by our whole is greater than part theorem. Okay, so I can claim that. It's one of our part-whole theorems, that the whole is in fact greater than the part, and no matter how many parts that whole's cut into, the whole will always be greater than that. So why is that important? Well, because if I can compare angle DFG to angle EFG, well, just above in step C, I know that EFG and EGF are equal in measure, which means I can take EFG out of that comparison and replace it with EGF, which is what I'm doing here in step E. So I'm concluding with some substitution. Taking EFG out and replacing it with EGF, that's just basic substitution. I know those two things are equal, which means I now have a comparison of angle DGF to this angle over here, EGF. So I'm getting closer to that comparison I want, that DFG is greater than DGF. Now, before we move on to the next slide, because there's going to be more on the next slide, I want you to remember here step B, that we know that AC and DG are equal. We're going to actually use that relationship in the next slide, okay? But that relationship will disappear, so just keep that in mind. So let's take a look then at what follows about our proof here. I'm going to carry our step E onto the next slide for us. All right, so on the next slide, we've got 5 more steps, or really 4 more steps. We've got step E ready for us already. That's substitution, that we know that DFG is greater than EGF. So now what I want to do is turn our attention to the angle EGF. There's something special going on there. Notice that angle EGF is cut into smaller parts. There's an angle DGE and angle DGF. There's our angle DGF. I can claim, since EGF is the whole angle, I can claim again that EGF is greater than angle DGF. Why? That's again our whole is greater than part theorem. Okay, that angle EGF being the whole is greater than any of the two parts. So angle EGF is greater than DGF. But now use step E and step F together to arrive to our new statement in step G, in part G, that if DGF is greater than EGF, DFG is greater than EGF, and EGF is greater than DGF, then I can claim that angle DFG is greater than angle DGF, which is exactly the comparison I wanted. And this is by our property transitivity of greater than. Okay, that if A is greater than B and B is greater than C, then A has to be greater than C. If DFG is greater than EFG and EFG is greater than DGF, then DFG has got to be greater than DGF. So there we have it, by transitive greater than. Well, what does that do for us? Remember, our triangle focus is right here. Well, now we have a comparison of angles within the same triangle. So I can compare the sides opposite. Look at the side opposite of DFG. It's side DG. Look at the side opposite of angle G here. This angle, sorry, DGF. It's side DF. So I can claim that side DG is greater than side DF. Why? Because of our converse of ATT, converse of the anisosceles triangle theorem. That if I have a comparison of angles within the same triangle, I can compare the sides opposite of them. What does that then conclude for us? Since DG is greater than DF, well, remember that part B from the last slide, that AC and DG are equal in measure, which means whatever is true about one is true about the other. So I can replace DG with AC, thus claiming our final statement that AC is in fact greater than DF by simple substitution. And there we have it, QED, the Hinge theorem, that if two sides of one triangle equal two sides of another, and the included angle of the first is greater than the included angle of the second, then the third side of the first triangle must then be greater than the third side of the second. And essentially, we can compare the sides opposite of those included angles. And so that's the Hinge theorem. Okay, we'll see some more application of the Hinge theorem in our very last lesson. But for now, we also want to continue to prove the converse of the Hinge theorem. Yes, the converse is also true. Now, you'll notice that in the converse, it starts off almost identical. In fact, it starts off identical with the side relationships. If two sides of one triangle are equal to two sides of the second, so we have to still have those equal sides going from one triangle to the other. But this time we change our given slightly to include in the comparison of the third sides, not the comparison of the included angles. So it says if two sides of one triangle are equal to two sides of a second, and the third side of the first is greater than the third side of the second, so we notice we have a comparison of our third sides, then the included angle of the first is greater than the included angle second. In other words, that included angle, the one that's sandwiched between our pairs of equal sides, that's the angles in which that we can actually compare. Let's bring our converse of Hinge to life. So here's our diagram. If AB is equal to DE and BC is equal to EF, meaning we have two sides of the first equal to two sides of the second, and we're given a comparison of our third sides, AC is greater than DF, then the angles opposite of those third sides we can actually compare. So we can claim, since AC is greater than DF, that angle B will be greater than angle E. Now we want to prove this to be true, okay? And actually the proof of this is quite simple because we already have proven the Hinge theorem. So let's take a look at how we're going to prove this one. We're going to prove this one indirect, meaning let's assume that since we want to prove the measure of angle B is greater than the measure of angle E, let's assume that it's not. So let's assume that the measure of angle B is not greater than the measure of angle E. What then does our assumption lead us to? Well, the law of trichotomy says that if it can't be greater than, then there's two other possibilities. That either angle B has to be equal to angle E, or angle B is going to be less than angle E, right? Which means we have to contradict both of those. So on our last slide here, so here's our two assumptions, right? B will be equal to E, and that B will be less than E. We have to contradict both of those. So let's take a look at our reduction. The reduction is actually very simple to prove here. Let's take a look why. So let's start with our first part, which is let's assume that angle B and angle E are equal to each other. So if the measure of angle B is equal to the measure of angle E, we'll take a look at our diagram first. Aren't those two angles just lovely? Look at those equal angles. All right, this is so beautiful. They're totally equal in measure, right? So if they're equal in measure, then what happens between the two triangles? The two triangles are then congruent to each other by side angle side congruence. Thus, by CPCTE, the length of AC has to be equal to the length of DF. But this contradicts the given. Remember that our given says that AC is greater than DF. So we can't have angle B and angle E be equal in measure. That won't work. Well, then let's contradict our second statement, which is that what if we assume angle B to be less than the measure of angle E? So if measure of angle B is less than the measure of angle E, then by the Hinge theorem, okay, what we just proved with the Hinge theorem, by the Hinge theorem, we know the side opposite of the greater angle must be the greater side. In other words, AC would have to be less than DF in this case. And again, that contradicts the given, because we're given that AC is greater than DF. So we toss out our assumption that angle B and angle B is not greater than angle E. That's false, because the two other possibilities each run into a contradiction, which means because our assumption is false, that means angle B must be greater than angle E. And that's the conclusion we wanted, to prove that we can compare those angles. And that's the converse of the Hinge theorem now. So QED, okay, we got that one. From this, we now have two beautiful theorems that actually allow us to cross-compare between two triangles. What this is going to lead us into is our very last lesson of this chapter, which will actually apply everything we've seen this chapter of our inequalities. So please be working on the 5.4 worksheet. It is a bit of a doozy. There's a lot to it. So please, if you do have any questions on that, don't hesitate to email me. With that, be good and do good.